Okay, hello everyone. Welcome to our National Science Week event, exploring gravitational wave detectors. Oh, sorry, start again. Hello everyone, welcome to our National Science Week event. It's called Exploring Gravitational Wave Detectors in Minecraft. My name is Dan Brown. I'm a researcher at the University of Adelaide in South Australia. Sorry, let's just get the Minecraft up. Sorry. I'm a researcher at the University of Adelaide in South Australia, and I'm part of the collaboration called OzGrav. And today we'd like to take you on a virtual tour of LIGO with Minecraft. And so this is an idea we've liked to try out for a while now, and this is the first time we've tried it, so we may have some teething and technical issues, but please bear with us if you're joining on with the tour in Minecraft. So I see we have a few visitors here with us today. There might be a slight delay in where I'm speaking and where I'm walking, so you might see me wander off if you're listening in on the YouTube channel. So yeah, so this world we've been developing for National Science Week. It's been developed by myself, several other researchers here at the University of Adelaide, including PhD students, master's students, and some undergrad students. And we're very grateful for the South Australian community grant for providing us some money to host this server, buy various Minecraft licenses, so we can actually finally realise this. So this virtual tour is for LIGO. LIGO is a big experiment over in the US for detecting gravitational waves. If you've never heard of LIGO before, hopefully by the end of this tour you will hopefully know a bit more about it. If you've ever been to LIGO yourself, then things may look familiar, they may look slightly different. Obviously this has been built by a group of researchers that have gone and spent several amounts of months working at the site, and there's also been sort of directed by these researchers to the students on how to build some of these rooms and parts of LIGO. So there's some creative licensing here. So for those who don't know, LIGO is the Laser Interferometric Gravitational Wave Observatory, and so that's a lot of long words to essentially say that we're detecting gravitational waves or observing gravitational waves using lasers or a laser interferometer. So the LIGO project has been running now for several decades, but it hasn't been up until fairly recently, so the 14th September 2015, where we made our first detection. So initial LIGO was built several decades ago, and then we went through a long process of building advanced LIGO, and we switched advanced LIGO on around about the 14th September, and not too long after we switched it on, we saw this signal coming out of the detector, is what you see here in front of us. So there are two LIGO detectors. We've got orange and blue here. There's one in Hanford in the USA, up in Washington State, and there's one down south in Livingston. And so we need two of these detectors so that if we actually see some signal coming out of our detectors, we can, if we measure the same thing in both of them, we know we've actually seen something, or we've measured gravitational waves. And so here on this plot, we can see the output, which we call strain. And on the time here, we can see it's only just a fraction of a second. But we see there's these two red and orange and blue lines. Oh no, gone part of the image out. Here we can see there's some oscillation building up of the wave. And you can see that this wave starts off slow, and we see these few oscillations building up, and they're in phase, and eventually they get faster and faster. They reach a peak, and then suddenly they disappear. So what's going on here? What are gravitational waves? And I'll take you through a couple of sort of slides or demonstrations here to hopefully explain that to you. So here, for example, we have an image of how we can visualize potentially a gravitational wave. So gravitational waves comes from two bodies orbiting each other, and they distort and bend what we call space-time. So space-time is what we live in. It's the three dimensions of space and time. So it's all up, down, left, right, backwards and forwards, and time. And so when we say that we're getting a wave, or gravitational wave is a wave in space-time, it's distorting and bending the space and the time that we live in. And you can kind of visualize this a bit as if you dropped a pebble or something into a pond. And you drop a pebble in, and you get these ripples that oscillate away from the source and radiate out. And as they're quite strong close to the source, but then they get weaker and weaker and weaker. So going over here, gravitational waves are slightly different from what you'd imagine on like the ocean or in a pond or some other kind of sort of like air for sound waves. They kind of have this sort of very odd looking sort of worm-like distortion going on. And so here we can see that there's a gravitational wave propagating from the right of this image towards the left. And you can imagine that we're living in some space inside this flat circle. And so if you were stood in here and there was a gravitational wave coming towards you, it would stretch you in one direction while simultaneously squashing you in the other. So you get taller and then you'd get thinner. And then as this oscillation changes around, you'd then get stretched outwards and you'll become shorter. And so this is what I mean by stretching and squashing of space and time. But of course, this might sound scary, but in reality, this distortion is incredibly small. We're talking like thousands of times smaller than even the size of an atom. And so this is part of the challenge in actually trying to detect gravitational waves, is they are very small. And you need very incredibly heavy masses to actually generate them in the first place. So looking behind us here, we can see an animation of two neutron stars. So neutron stars are effectively dead stars that are left over, and they're incredibly dense and heavy. And as they oscillate around each other, or orbit around each other, they will radiate these gravitational waves out into space, and due to the conservation of energy, as they radiate out energy, they lose some gravitational energy. They lose energy and get closer together. So as these get closer and closer and radiate more and more gravitational wave, it gets to a point where they collide into each other. And then we see incredibly sort of violent astrophysical events, such as like supernova, as you can see here, which give off incredibly bright flashes in the night sky that hopefully we can observe with telescopes. They're also another type of source. So down here at the end of the corridor, we can also see black holes. And so here we can see two black holes just steadily orbiting each other. And in the middle, there's these black areas where no light is able to escape. All the light's being sucked into this black hole. But we can see that in this background of the image, there's all these stars in this galaxy. And then as the light is sort of passing through, going past these supermassive black holes, these heavy black holes, they get bent and distorted. And you can see that these stars are now being distorted as these two black holes move around each other. So going back down to, now we've got enough rough idea about what gravitational waves come from. These are the types of signals that we're looking for, and they're incredibly small. Where in the night sky do they actually come from? Well, they come from all over. If any of you have been lucky enough to see the Milky Way in all its glory in the night sky, you'll see it's actually pretty big. It covers quite a lot of the night sky. And these colourful rings here sort of describe where we think we've seen these gravitational waves appear from. And so you can see GW 150914 in this sort of cyan, tealy colour. We think it came somewhere. The black holes that collided were somewhere in this region, which is quite big, and obviously that's quite difficult for us to then say, astronomers, please point your telescope in these directions into space and have a look. It takes a lot of time to explore this sort of vast area of the sky. And you can see that we detected a bunch of other signals, various other ones through the year. So obviously these first two numbers are the year, this is the month and the day. So this is 2017, 2015, 2015, 2017. And you can see again, some of these are even larger, and they're very large parts of the sky. But we're getting better, and the better that we make our detectors, and the more of the detectors that we build and place around Earth, we can actually make these areas very much smaller. And so you can imagine this a bit like triangulation, where if you've got lots of different detectors in different parts of the Earth, and you can see when the signal will rise at the detector, you can better sort of pinpoint where in the sky that's coming from. So you can see for GW 170817 and 170814 down here, we've actually got a pretty good idea of where those come from in the night sky. But it's still relatively large, so we'd like to get that smaller a bit better. So how do we actually go about detecting gravitational waves? If they're so small, smaller than the length of an atom, we need an incredibly sensitive detector to be able to measure this. And we can use this, we can do this by using another type of wave, or light. And so here we've got an experiment which is called the Michelson interferometer. This is where the interferometer comes from in the LIGO name. And here we have a laser, and this laser shines out some light. It hits this optic here, which we call a beam splitter, which splits the laser in half effectively. It sends half of the light traveling up what we call this arm, and sends the other half down this arm. As the light propagates down this arm, it hits a mirror, and it will be reflected back down again towards the beam splitter. Same for this arm. And so depending on how long it takes for the light to propagate up and down these arms, and up and down this one, because it's a wave, when it comes back, it may be what we call in phase or out of phase. So in phase or out of phase, if they're out of phase, this means that a trough lines up with a peak. And when you add these two waves back up together again, they cancel each other out. No wave detected. However, just like we showed in maybe this animation over here, what we're seeing is gravitational waves stretch and squash space. And so from this diagram, we can see that as a wave comes in, it will stretch one arm and squash another arm, and then simultaneously stretch this one and squash the other. And when this happens, when the laser light comes back out again, we see small flashes on our detector. And this is what this graph here shows, which is the small oscillations in the signal that we measure. So now I'm going to take you past the offices. So this the office area is mostly where all the scientists and engineers sort of sit and have their offices and work on problems. As we go through this area down through the doorway, we shall see we go through this nice corridor. This corridor looks a lot better here, I think, than it does in real life. In real life, it's just a white corridor, but we have some fantastic artwork by Osgrav artist Carl Knox. And so here we can see Einstein overlooking two supermassive black holes orbiting each other with their accretion disks. And so now we get past the offices and we get more to sort of the engineering part, or the heart of the interferometer. So walking down towards the left, we walk past the control room, which we'll go into and have a look in more detail in a second. But I think to start with, we'll just do a flyby to give a scale of how big LIGO is. So from that animation we saw with the Michelson interferometer, we have a beam splitter and we've got these two arms. In reality, how big is this? LIGO is a huge experiment. This is big science. And these arms are 4 kilometers long. And so the longer we make these arms, the more stretching and squashing that happens, and the bigger the signal we get. And so 4 kilometers is a reasonable length. In the future, we might want to make them even larger. But for now, this is what we have. And so in the center here is where, in that animation I showed you, where the beam splitter is, and many more optical parts and components, which we'll go and see later on. But here, going up and down, is the arms. So let's just take a quick shoot down the arms. So the detector that we've kind of based our model on here is the Hanford detector. So Hanford is up north in Washington State, just a few hours from Seattle. And it's in a very sort of dry, deserty-like environment, which is kind of what we tried to replicate here in Minecraft. And as you can see, we've just flown past up this arm. We see this mid-station, which is obviously the middle part of the arm, and there's some vacuum components and sort of access points in there. And then eventually we get to the end, or the end station. And so this is where the laser light will bounce all the way down here. It will reflect off a mirror down in here, which we call the end mirror. And it will then be bounced straight back down to the central corner station again. And so we can't just bounce this laser light into air. It's actually has to be much more protected because of the size of the signals that we're actually trying to measure here in LIGO, and 10 to the minus 19 meters of displacement. We need to make sure it's isolated from all the kind of noise, seismic motions, wind blowing, everything effectively. Once we've isolated the experiment from all these different types of noise, then we can just start seeing gravitational waves. So what we can see is these arms are actually just a concrete tube, but these are really here just to protect this stainless steel tube, vacuum tube down here. So a vacuum is essentially an area of space where we've sucked out all of the particles and contents in there. So there is nothing in here. This is an ultra high vacuum, and the laser light can bounce up and down this tube unimpeded. It won't hit particles or dust or air and get distorted or scatter around. So, flying back down again. This concrete tube is actually quite important. Obviously Livingston is down sort of down south in a much more swampy, wet area. And so each one of these tubes kind of have to deal with sort of different issues. Down south there's obviously problems where they can get wet and can get corroded. Up in Hanford, for example, this is quite an open area, and it's actually near a nuclear power station. And where there was one incident several years ago where there was one of the local police, I believe it was police or nuclear station police, were essentially driving around monitoring in the area, and they actually just drove over one of these hills in the middle of the night. Just drove straight into the concrete tube. And so luckily the concrete tube was there to protect the vacuum, because if the vacuum breaks, then LIGO would suffer dramatically. So one of the other sort of interesting points, if anyone's ever been to the LIGO Hanford site, is they have an incredible problem with tumbleweeds. So I'm sure a lot of people have probably seen tumbleweeds in various movies. Normally when they're sort of empty and eerie and nothing's going on, you just see a tumbleweed sort of just blow past in the wind. But Hanford has a lot of tumbleweeds. There's not just one. The whole area, it seems to be covered in them. And these can actually build up and pile up significantly, and actually need to be cleared out fairly regularly. For example, here, they've built up to the point where they're significantly higher than the car. And so there's special tractors to actually go out and drag all these tumbleweeds away and to keep the areas clean. So we've got a few tumbleweeds knocking around in our Minecraft world. In reality, they end up on the roofs, they end up in all sorts of places, so I'm sure we'll see many of them. So now we'll fly back in and we'll have a look at the control room. So here in the control room is where is the beating heart effectively, and where all the monitoring of the instrument is done. So this area over here is what we call the operator area, and so this, when the detector is running in what we call science mode, as in it's sat there listening quietly to any gravitational waves that might be passing by, an operator will be here 24/7, monitoring the detector, looking at all these various screens to make sure that nothing's going wrong, and if something does go wrong, try and fix it or call someone in to make sure that it's, that we can keep on observing. So these images that you see are actually screenshots that we managed to take. Some of these are only a few days old, some of these are probably a few weeks old, but these are the actual screens that you would see if you were going on the actual tour at LIGO. And so just to go through some of the more interesting ones, for example, so here, for example, is one of the earthquake monitors, and so if there's any serious seismic sort of motion around the site, this can obviously disturb our detector significantly, and it can also shake the detector so much that it actually stops the whole thing from working. So we have to be careful when big earthquakes are coming in, especially, and try and put the interferometer in what we call sort of this safe mode. So here, for example, we see that there's just this steady amount of seismic motion sort of bobbling along, not much happening, and then suddenly a big earthquake is hit, and then this earthquake can take several hours, so this time scale here is on hours, to sort of ring down and quiet down. We can also see that, well, sorry, you can't see in this plot, but we also have this big problem here, is that we get these micro-seismic waves that travel through the Earth's crust. And so LIGO Hanford is probably a 5-hour drive in from the coast, the Pacific coast. But if there's a big storm brewing in the Pacific Ocean, then the waves that are crashing into the beach or into the continental plate actually shake the ground enough that this actually disturbs and can make running one of the LIGO detectors actually quite hard. So here it's actually quite a quiet time, but in particularly stormy and windy conditions, this might rise up significantly. So we also have some more sort of diagnostics and tests, sort of monitors that are going on. We also have a scientist here who, for some reason, is stood on top of a computer, right in the way of one of the plots I wanted to talk about. This here is a plot of the actual sensitivity of the detector, and so you see this red line here is what LIGO Hanford, the sensitivity was on 22nd of July 2020, so a few weeks ago. So this is currently what it was running at. Yellow and blue here are what the sort of the best sort of sensitivities that have been running at, and this is where the sort of sensitivity we'll be operating at for listening to gravitational waves. So the lower this curve, the better, effectively. And so because this red curve is a bit higher, this could just be because at the time we weren't in sort of science run, sort of science observing mode, and there's probably lots of scientists and engineers working on things or trying to debug the detector and make it better. So the actual LIGO detectors are currently going to go, have stopped observing. They stopped observing back in April for what we call O3 or observation run 3. And now they're going to switch off for a couple of years, and we're going to be upgrading them to hopefully make all these curves here a little bit lower so we can see sort of further out into the universe. We also see over here, we see lots of sort of status and updates. Obviously anything that's red typically means something you should probably look at and check out. Green things are good, red things are bad. And we see lots of screens here, for example, showing how much laser power is being generated and injected into the infrometer, how much laser power is actually finding its way into the infrometer. And you can see here there's some like red signs here to say that some of the suspensions aren't operating at the moment in time. Other red parts here saying that this optical cavity isn't running. And so this is an easy spot where the operator can sit, monitor everything, and figure out what's going on. So you can see also we've got these two clocks up here. This green one is what we call GPS time. And so because we're operating with scientists from all over the planet, and we're obviously interested in exactly when we measure certain signals. I mean, if we're really interested in when a certain signal comes in at various points all over the world, then we make sure we have to use the right time. So obviously, over this time, we just got the local time. So this is 12:30 in the afternoon, and this is GPS time. And so this is some clock when that sort of counts up second by second ever since GPS has been switched on. So let's have a walk down the corridor. And so here on the right, we just have some computer rooms. There's also lots of servers and computers that are used to control all the interferometer and keep things running and ticking along smoothly. We have electronics rooms, for example, where a lot of the equipment and electronics is built before it's getting installed in the detector. And we get to this area down here, which if you're actually going on the tour yourself at LIGO, this is actually kind of where you would veer off down this way and go outside and have a look at the sort of surrounding area. However, because we're in virtual LIGO, we can actually now take a step into the actual what we call the LVA, which is the laser vacuum enclosure area. And the first step here, before you go in here, because we need to keep everything clean, you always have to make sure that everything's that you clean yourself up and wear protective gear. So we have like this nice foot cleaner here, which you shove your foot in and it brushes all the dirt off. As you come through, there'll be various areas in which we could sort of call garb up. And the idea is you go in looking something a bit like this. And so you have hairnets, masks, and clean room coats, gloves, special booties to make sure you don't traipse mud around everywhere. And this is all to protect the instrument from us as humans. So the instrument itself is not sort of dangerous to us per se, but we're particularly dirty. We get like if we drop hair or like dust or anywhere in the interferometer, that might cause problems. And so we want to try and keep it as clean as we possibly can. So there are a lot of areas around the back here which you can explore once you're if you want to log in. And these are optics labs. But for now, we'll go through into the LVA area. And so as we come down, we'll walk into the main part here. So this is the heart of the one of the LIGO detectors, LIGO Hanford. And if we zoom up over here just to get a little bit of bird's eye view. This is quite a packed area and there's a lot of stuff going on. So all these big volumes here are the vacuum system. So this is what protects all the optical components inside. In this area over here, we have what's called the pre-stabilized laser, which we can see here in this picture. We have 3 engineers helping to build what we call the PSL. And so in here is where the laser light is generated. And at the design power, hopefully we should be outputting 125 watts of optical light at 1064 nanometers. And that's the wavelength of the light. So obviously, as it's a high power laser area, things have to be clean. So, I mean, you have to be clean to get into this LVA area, ideally. But if you want to actually go in and look into the place where into the actual pit, more researchers standing on top of computers. Wonderful. And as you're in the PSL, this is a very clean area because any dust and high power laser would quickly start burning and causing problems. And so this laser is generated on a table such as this, and then it's injected and goes down into the vacuum system. Yeah. So as when the laser light comes in, we go into one of these big volumes here, which we call the ham chamber. So each one of these has got a name. This is ham 1, this is ham 2. Ham stands for horizontal axis module, which is a bit of a mouthful, which is why we just call them hams. And the internal of the LVA looks a bit like this, just to give you an idea. So we can see that we have these small ham chambers joined up to by large pipes between the other ones. And these big chambers here, which is called the beam splitter chambers, which is where they house some of the bigger optics. So these blue piers here are part of the seismic isolation system. So these are the first stage of defense against any kind of seismic motion. We can see these here. So each one of these big vacuum tanks are supported by what we call HEPI, which is a hydraulic. It's like a hydraulic suspension isolation system. So as we fly down, we can actually see inside. Let's see what inside one of these chambers look like. And so inside there's this another optical table, which is where we place all the optics. And so these are like combinations of mirrors, lenses, photo detectors for measuring the signals, laser signals. And at the end here, down at this part of the interferometer, is actually where the gravitational wave signal comes out. So on the flashing light that we saw in the animation, this is where we'd measure it, and this is where the gravitational wave signal actually comes out. So down in this part of the detector is where a lot of researchers from Ausgrav have been busily working away over the years. Here we see 2 researchers from the Australian National University installing some new equipment in the vacuum in the part of LIGO down here called it's a quantum squeezer, which helps to improve the sensitivity of the detector. So now if we go up, so just to point some things out, here is one of the chambers, which is where the beam splitter lives. And we can see as we go up this way is one of the arms, which goes off and flies up towards the X arm. And then as we go over here, we can see the other tube, which goes up and goes all the way up to the Y arm. And so the laser light will come down. It will come out of the laser, the PSL. It will come to the beam splitter, be split, and then sent off all the way back down and come back down to combine them. So to protect the mirrors, some of the people on the tour, to protect the mirrors from seismic isolation, we obviously have these blue pre-isolation stacks to protect from seismic motion. But then the next stage of defense is what we call this initial suspension isolation system, or an ISI. And so each one of these lives in this top area here of these vacuum systems, and from there, this is where we hang the mirrors that form up the LIGO interferometer itself. And so here with these incredibly expensive mirrors, some of the most expensive mirrors on the planet, and here we can see these up close. And so you can see that there's this frame here which holds up these mirrors. Here is what we call the test mass. So this is the one where the laser light bounce on and reflects off of. But all of this is suspended from one of those isolation systems at the top, and they hang down from several stages of pendulums. So at the top, there's going all the way down to the bottom is 4 stages. So this is like having 4 pendulums, one suspended after the other, all going up. And each stage of suspension helps us suppress the seismic motion even more. And so it's these amazing feats of engineering that allow the LIGO to be kept so quiet that we can actually measure these, even though there are people walking past, trucks driving past, or small earthquakes. We still operate. And so here we can see this in our vacuum chamber here. We can see this has been opened up. We're actually, when you open up these chambers, obviously we have to keep them clean again, so we have to make sure that we're properly cleaned up. And there's also, you have these big clean room tents that sit around the open chambers. And so these will force clean air in and so make sure all the dust is blown out. And so here is one of the suspensions, and if you want to, you can, once you're exploring, you can actually go and jump around inside the vacuum system and have a look around. So there's a lot more going on here, and you can see there's a lot more extra tubes. So in Hanford, there was actually, once upon a time, 2 interferometers. So we have LIGO, Hanford, which we call H1, and this is a 4 kilometer long interferometer. But there was also set up back in the day was called H2. And so the idea was that if you run two detectors at the same time, you might be able to see gravitational in one of the this gravitational wave signal in both interferometers at the same time. But over the years, we've realised that it's probably better just to focus on one, the 4 kilometre long detector, and the H2 detector has effectively been decommissioned. But it's not the end of the life for many of these components. Most of these will actually head off to LIGO India. So most of this was being disassembled now, and it will be shipped over to India to be installed to form another 4 kilometre long detector. And each one of these we've built up to form another LIGO that will be operating in India, hopefully over the next decade, and offer us even more sensitivity. So here we can also see what it's actually like to be inside one of the vacuum chambers. These chambers are actually pretty big, to give sort of a scale of how big these are. We've obviously tried to build this virtual map for a tour to give sort of a sense of the scale of the whole experiment, which is obviously kind of hard when you've just got pictures. But here you can see a scientist stood in here, so these are like 2 meters wide. And here they're installing some baffles, and so these baffles you put up to stop bouncing around off things that shouldn't bounce around and get back into the interferometer and cause issues with that. And again here we can see another image of the LVA, and we can see we have these long tubes, obviously of the beam splitter, and here we have H2, and then all the various sort of parts and electronics going around to make sure all this works. So this concludes our tour pretty much of the LIGO interferometer. I hope you've enjoyed, and this is given you kind of a good overview of what the LIGO detector is, sort of how big it is and the scale that we're operating at and the various different components. Obviously we'll still be online on the chat if you want to ask any questions, and feel free to log in and have a look around this world yourself, have a poke around. Obviously there's lots of parts that we haven't shown, which we're hoping you're going to go and have a look at yourself. So thank you very much for coming along, and enjoy exploring our virtual LIGO.